Okay, let's dive right in. We're opening a cold case file today, but our mystery, well, it isn't set in some dark alley. It's locked inside a block of one of the toughest metals on the planet. This is a story of engineering pushed to its absolute limits.
And that brings us to this central question, right? The riddle that has frustrated engineers for decades. We're talking about a material that's a cornerstone of modern tech, but it guards its secrets fiercely. It makes it almost impossible to work with.
All right, so let's meet the main character in our story, titanium alloy Ti-6Al-4V. Now, that name sounds pretty complex, I know, but it just means it's about 90% titanium, 6% aluminum, and 4% vanadium. You've definitely heard of it, but you might not know its dark side.
You see, this alloy has a total Jekyll and Hyde thing going on. On one hand, it's the hero. Unbelievably strong, super lightweight, and it basically never corrodes. But the second you get it in the workshop, it becomes the villain. A notoriously difficult material that traps intense heat, chemically attacks the tools trying to cut it, and fights you every step of the way.
And the stakes for crack in this case? They could not be higher. A staggering 80% of this alloy is used in the most critical aerospace parts you can imagine. We're talking jet engines, aircraft frames. When components like these are involved, failure's it's not an option.
So, faced with this massive challenge, a team of researchers launched a really meticulous investigation. Their whole mission was to find this alloy's weakness, to crack the code that would finally make it give up its secrets.
You know, every good detective needs a method, and theirs was this powerful statistical tool called the Box-Behnken design. Think of it like a clever way to systematically interrogate the material. It lets you test all these different combinations of factors really efficiently, to find the one that just breaks the case wide open.
The investigation zeroed in on 3 key suspects, the variables that could make or break the whole operation. First, you've got cutting speed, that's how fast the tool is spinning. Then there's feed, which is how quickly it moves into the material, and finally, step over, the distance between each cut.
Their game plan was this really rigorous 5-step process. First, they defined their suspects. Then, they designed a series of 15 intense experiments. And then, they went to the crime scene to machine the titanium and gather all the evidence.
And over those 15 runs, they collected a flood of forensic data. They were meticulously measuring surface roughness, looking for that perfectly smooth finish.
They captured the incredible cutting forces being generated, forces that are strong enough to snap a tool in a heartbeat. And they recorded the extreme temperatures that build up in just seconds. Heat so intense, it can literally destroy the cutting edge and ruin the whole part. The evidence was definitely piling up.
So after sifting through every single data point, analyzing all the evidence, the investigation had its first major breakthrough. They found a pattern. They found the formula.
And here it is. This is the code they cracked. For a standard tungsten carbide tool, these were the magic numbers. A really high cutting speed of 3,000 RPM, a feed rate of 179 millimeters per revolution, and a shallow stepover of just half a millimeter. This was the optimal recipe. And just like that, it really felt like the case was closed. But, in every great mystery, there's always a twist. The researchers started asking a new question. Okay, we have the right technique, but do we have the right weapon?
And this is where we get to the final act, because the investigation was far from over. 2 new contenders were brought in for a final showdown. In one corner, you have the high-tech coated tool, armed with this special layer of aluminum titanium nitride for extra heat resistance. And in the other corner, the cryogenic tool. This was a standard tool that had been put through a deep freeze treatment at minus 190 degrees Celsius, a process that fundamentally changed its internal structure.
So the stage was set for one last decisive test. All 3 tools, the standard, the coated, and the cryogenic, were going head-to-head using those optimal parameters the team had just discovered. It was time to find the real champion.
And the first piece of final evidence came in, surface roughness. Now, the coated tool was a little better than standard, sure, but the cryogenic tool, it was in a completely different league. It produced a dramatically smoother, higher quality surface, and that means a stronger, more reliable part. Next up, the force required to make the cut. And again, the cryogenic tool was the clear winner. It was slicing through that tough titanium with way less effort. And what that means is less stress on the machine, longer tool life, And at the end of the day, a cheaper and more efficient process. And here it is, the final, critical clue. Remember how we said that heat is the #1 enemy when you're machining titanium? Well, the cryogenic tool ran substantially cooler than both of its rivals. That is a massive advantage that translates directly to better precision in a tool that lasts way longer.
So when you look at all the evidence, it's overwhelming. The case was finally, definitively closed. For machining this impossible alloy, the cryogenic tool proved to be decisively superior in every single metric that matters.
But look, this discovery is so much more than just an interesting finding in some lab report. This represents a genuine revolution in how we make things, especially the really important things that keep us safe up in the sky.
I mean, listen to how the researchers themselves put it. This isn't just an improvement, it's a revolution. By solving this case, they've paved the way for a future where making these critical aerospace parts is faster, cheaper, more energy efficient, and most importantly, more reliable.
And that leaves you with a final fascinating thought, right? This entire industrial cold case was solved not by applying more force or more power, but by a radical change in temperature. It just makes you wonder, what other unsolvable problems out there are just waiting for us to look at them from a completely different, maybe even a colder perspective?